In the last video, we did theorem 4.3.1 from a geometric standpoint. In this video, we're going to look at the same theorem from an algebraic standpoint. So let's refresh our memories as to the statement of the theorem. So let f of xy and g of xy have continuous partial derivatives in some open set containing the smooth curve g of xy equals k for some k in R. And remember that g of xy equals k can be interpreted as a level curve of the surface g of xy. If f has a local extremum at AB when restricted to input values that are on the curve g of xy equals k, and if the gradient of g at AB is non-zero, then there is a real number lambda such that the gradient of f at AB is lambda times the gradient of g at AB. As I said before, we did the geometric standpoint, a geometric justification in the last video. Let's go and look at an algebraic justification. So first of all, let's assume or suppose that our curve g of xy equals k can be parameterized. With some function r of t as x of t and y of t. So g of x is supposed to be smooth, g of xy is supposed to be smooth, so r of x, y will be differentiable. Then h of t, which is f of those two input coordinates, so x of t and y of t. Well, if you plug these points into the function, you're getting the image, and h of t represents the height of that curve. So h of t represents the height of the image curve of g of xy equals k on the surface of f. Which means that when f restricted to the values of g of xy equals k has an extremum, then so does h. So if f restricted to g, so if it has an extreme value, this is also an extreme value of h. So let's assume at this extreme value, so let's assume that f does. And that this is one of the cases where h prime is equal to 0 there. By the chain rule, dh dt, which is h prime of t, is del f del x times dx dt plus del f del y times dy dt. Well, if this is equal to 0, del f del x and del f del y, that's the gradient of f. dx dt and dy dt, that is the derivative of r. They are equal, or their dot product, right? This is what we have up here. Their dot product is 0. If their dot product is 0, So the gradient of f is perpendicular to r prime. R prime, you remember, gives the direction of a curve. And so if our gradient vector is perpendicular to it, I might draw it something like this. Now this curve is the curve g of xy is equal to k. And therefore the gradients of g, or gradients, are always perpendicular to level curves. So the gradient of f is perpendicular to r prime. The gradient of g is perpendicular to r prime. And therefore these two vectors, which are perpendicular to the same vector, must be parallel. And if they're parallel, then they are multiples. So, a quick note. Theorem 4.3.1, whoops-a-daisy. Theorem 4.3.1 does not guarantee the existence of extrema. In fact, the existence of a local extrema is one of the assumptions, or hypothesis. We assume it exists and then draw a conclusion. If no extremum exists, then the theorem does not apply. And people very often forget this and apply the theorem and draw a false conclusion. The existence of extrema can be guaranteed by other theorems, potentially. Notably, one that we've seen recently, the extreme value theorem. Under the right conditions. In the next video, we will see how to use the theorem to implement a method of Lagrange multipliers, and we'll do an example where we'll apply that method.